today we're going to talk about the drone challenge. So yeah, what's the drone challenge? I don't think we have to go over this because I think it's pretty clear right now. So you can skip this slide. Yeah. So the requirements of the drone is that the drone has to pick up litter. It's a plastic can and a glass bottle, and it has to detect this litter with an AI vision system. And it has to differentiate between these two types of litter. And that's done by an AI vision system. And it has to count the total amount of pieces of litter on the ground. So the drone flies over a piece of ground and it has to count the total that it sees. Yes.
Yeah, okay, so for the drone, we got a standard kit like everyone here. We decided on a driving mechanism. So the remote controller mixes, it has a switch on it, and when you flip the switch, it changes the channel, so it disables all motors. It disables the propellers, and it uses the right stick to mix the signals, so you have differential steering for the car mode. It also has a couple of flight modes, so GPS mode is very useful for staying in one spot, so maybe it can also be used for a pre-planned path to detect trash. Yeah, that's about it for the controlling of the drone.
So for the AI system, we obviously have to train it. This is done by taking lots and lots of pictures of the litter. And then you have to annotate them, and we used a site called RoboFlow to annotate these pictures. And then you can pre-process these images by changing the color so it's more sturdy when you apply your vision system in the real life. And yeah, let's go to the next one because otherwise we'll run out of time. So obviously there are lots of AI systems. I see that most of you uses YOLO. We have taken a look at some other AI systems like RetinaNet, but we had to make a test script to compare these two systems. So we made a test script for that. Yeah, so you can see here the test script. We can take a pre-recorded video. And then you get this screen, and you can change. These are all our models that we have trained. You can see the total cans, total glass, total plastic, and you can change the confidence score. So this is all done in real time to compare these two models.
Okay, so we tried several different cameras. We first started with the analog camera because they were available here at the BIC. As you can see, the quality is very, very bad. It has a lot of different flickering and color artifacts. Then we switched to the ESP32 camera. This is a lot better in color definition and stuff like that, but the lens isn't very good. It's a very cheap, very small plastic lens. So we had a lot of distortion, and we also found out that it really doesn't, it can't really withstand the vibrations of the drone. So we decided to use Joost's phone with Droidcam. We just basically attached the phone to the drone and use a app that sends the video signal over Wi-Fi to the laptop. The laptop then processes the AI, does all the AI stuff. As you can see, the video quality is much, much better than the other two options.
Yeah, so this is our final AI model. You can see the phone is attached under the drone, and it counts the total amount of glasses. So you can see the detection is flickering a bit, but here on the bottom left, he counts the absolute total amount of trash, and it keeps this. It keeps the tag of the bottle. So we used a software called Object Tracking, and this is our final product. And now for the gripping mechanism, it's your turn.
Okay. So, well, for the gripping mechanism, we made two separate presentations because we're of the mechanical engineering department, so we thought it would be easy to split those things up. Well, the whole process goes like this. The drone flies towards the trash, lands close by, drives to it, and drives above it. The gripping mechanism closes, and then it can fly away. So, the materials.
For the materials, we started using fast PLA because it was the most affordable option. But after a few tests and running, we decided that it wasn't satisfactory. So we switched to Reform PLA. It's PLA made of recycled material. It's a bit more expensive, but it's more sustainable and it's better printability. So that's what we eventually used for this. For the parts, we split the mechanical part in two. So we used the driving mechanism and the gripping mechanism. You also see it on this, it's two separate compartments. So I'm going to tell you first about the gripping mechanism. For the gripping mechanism, we have the base plate, servo motor, the gripping arm, and the shaft with the shaft ends. For the servo motor, we used this one, but last week we switched to a different type of motor. That's because this one has a 360 degrees rotation angle, and we found out it would be much easier to use a motor that had a 180 degrees turning angle. Also for the programming. It has almost the same specifications. The torque was enough, so yeah. Then for the shaft, we got a vormgesloten transmission. So we have in the gripping arm, we have a rectangular shape, and then the shaft is the same rectangular shape, so it can bring over all the forces and the torsion. We printed it in lengterichting, so it's better for bringing the forces. It doesn't break as fast. And then for the arm, you don't see it on the picture because this is a 3D model. It's hard to draw in 3D, but you can see. Oh, that's the battery. You can see it here. Yeah, we used elastics based on tests because we've done a few tests without the elastics and a few with. And what we noticed is without the elastics, because of the vibrations, the glass bottle will drop. This one will just do this, like translational motion. Yeah. The base plate is a pattern for attaching. And you got one arm that's static, so you got one moving part, so there's less risk of damage.
So now going to the second part, the driving mechanism. The focus was keeping it simple because why make something hard if you can keep it simple? So it's from a few components. So we have of course the motors, the wheels, the frame, and the connection plates. I designed it like this so you can print everything easily and don't have too much support. Because, well, if something breaks, you want to print it again without any problem. And, well, if you use a lot of support, that uses a lot of material, which is no good. So, for the attachment plate to the mechanism, this is where I get really excited from these things. This is what's the highlight of my project. So, you use these to put them into the attachment plate, so you can easily screw M4 bolts through it without needing any nuts and stuff like that. So it's you melt it into your 3D print. which makes me very happy, which I find very satisfying. I just want to make that very clear. So, and after that, I used the hexagon form to be able to put the rest of the frame easily in it to circumvent aligning issues. So you can put it in and have enough surface for glue, so it will be strong and won't be taken apart that easily. Well, then we've got the frame itself. You can see again the hexagon. Now you've got the male end instead of the female end, so you've got the hexagon shape, so it's easily put together. I made a perfect fitting housing for our little servo motors, which I will talk about just in the next slide. And this didn't go good in the first time, so I missed this notch here, so my cable couldn't get through, so I couldn't put the engine in. So now I fixed it. I put a little slot in there so you can push it through now, and it's clean, and it fits good and nice and doesn't have any other problems with rotating the engine or vibrating the engine in the housing. So as you can see, the fitment's pretty good, and we did some calculations of how much torque we needed. Well, that was very little torque, so we just chose the most basic servo motor, which was advised by our ETK students, because they said, yeah, we've got a PWM controller on board. Otherwise we need another, I don't know what's it called, another motor controller, I think. What was the problem? I don't know. Yeah, otherwise we need another motor controller if you wanted to use a DC motor. So they said, yeah, it's easier if you buy servo motors. Okay, well, we'll take that advice then, and then we'll go along with that. But well, the lightest one that would go 360 degrees in rotation had already a couple from or a torque capacity from 0.2 Newton meters, so that was way more than enough. Well, before the questions, I just want to talk about the wheels again. We chose to buy the wheels instead of make them from a 3D print. This could be a cool thing to do, to 3D print them as well, because you can do different kind of shapes and maybe put scoops on them if you're gonna go in high grass, so your scoops dig into the grass instead of your flat wheels, or make them wider so you float on top of the grass, so to say, so you have less pressure down. Other thing is, talking about slip in the last presentation, if you want to circumvent that, you can use Omni wheels. They use slip to their advantage to steer, but that's well, that was another thing we could have looked at, but we didn't. We did for further research into that, because they are big, lumpy, and I didn't think in grass and muddy situations they wouldn't work as good.
Yeah, and we got one more thing. The back plate.
Okay.
We edit that later. This is the back plate. The use of this is when you have a glass bottle. We want the center of mass to be in the center of mass of the drone. So this is perfectly aligned. So I calculated the center of mass of the glass bottle. And then when you put it against this, so it drives over it and then it stops. And then the center of mass is aligned. Yeah. So that's it.
Any questions?
No, first we would like to ask you to do the demonstration based on the resulting task.
Oh, team hè, team.
Sorry, je moet mensen hun werk laten doen wat ze kunnen. Hè? Staat met plastic flesje, want die doet het sowieso.
Ja, die beginnen met glas.
Even, jullie zijn team 1 en jullie beginnen met glas.
Plastic.
Oh, plastic. Sorry.
Oh, ik kan het zeggen.
Plastic.
Ik moet de controller afverbinding maken en dat hij het kan afwezen, dat hij dat doet. Ja, even bedenken. Nou, we kunnen met het wheel on the backside is used to close and open the gripping mechanism.
Yeah.
Then this switch is used to switch between flight and drive mode, and then this stick is used to drive. Gripping mechanism is closed. Okay, so we can drive over the bottle.
Yeah.
You
You push it
Yeah,
to the
yeah.
back.
I can't see much. So okay, so then we close the thing.
Yeah.
Then it
Lift it.
stays in.
Great.
Awesome.
So plastic is at 1 point.
Well, this also don't
Yeah.
know why it's beeping,
Easy.
but
Yeah, why is it peaking?
I have no clue. It's gonna explode in
5, 4, 3.
That's how we eliminate the trash.
Yeah, okay, the heavy one.
Okay, good luck, team.
So we drive over, we close the gripper,
Yeah,
Nice.
keeps it perfectly in place.
perfect. So, 3 points. You've made it. Great.
Very well. Very well.
Very good.
Good. Nice.
No questions,
The
denk ik,
next
hè?
step, the questions. I would like to ask Pavel and Thijs to ask the questions shortly because we are running out of time.
Yeah, I have a very simple one. When I look in the servos, how easy is to exchange them because they so quite often they broke.
You take the wheel off and then you can, it's one screw and you take it out. You slide it out.
Okay, so it's just slide
Yeah,
inside
so
out and
take
you
the cable
screw
off, slide it off.
from the shaft to the wheel.
Yeah, you can, if you look close by, you can see it. Like, okay, you have to take the wheel off, but there's only one screw in there everywhere. So maybe you can even reach it with the wheel on. And you can just slide it out like this, but you have to take the cable
The
off.
wheel stays there and you just put it.
Yeah, you can take it out like this, but if you change the servo, you need to change the wheel as well, so you have to take it out anyway. So if you do it before or after, it wouldn't be
What about the gripper? You use these rubber bands, and that's okay. That's perfectly fine. But I don't understand why you need them, because other groups they didn't need them. Can't you make the gripper make it grip the bottle more, so you don't
Can I
need to?
answer the question? That's right. Sorry.
No, okay.
That's right. You're right. You can make it close more. For our gripping mechanism, we wanted to open wider, which meant we had to make this extra angle. And probably if you have two moving parts together, because this one's static with this, if you have two moving parts together, you don't need it because you can close it together. But because one's static, the other one has to push it in. And if you want to make this wide, well, we needed to add this extra angle.
One problem is also that
And we didn't want
drones
to put it
fly forward by tilting. So if the bottle isn't gripped with an elastic material or something, if it tilts forward, it just slides out. So it needs some kind of elastic material that closes tightly around the object.
Okay. Again, it's not a problem.
No, okay.
It's just a good solution. About the question about slipping the wheels, there was the question for the other group. That was not the solution I was looking for. So
because only wheels were pretty good.
I was looking for a more simple solution, but you
Well-
don't get to answer that one.
We could just
Um,
take the rubber wheels off.
About AI, I think it is a good idea that you compared a number of different systems. But maybe I missed it. What was your conclusion? Is there one that stands out? That's the best?
So yeah, so there are two AI backbones essentially. So we've tested RatinNet and YOLO, and then we've had multiple versions of those backbones. We eventually chose YOLO because we've optimized it so that it can reach up to like 75 FPS. So that's really high, and that's absolutely needed if you want to track the objects. So then you can count the total objects on the grass field. And RatinNet can get a max of like 7 FPS, and then it's really harder to track the objects correctly.
Okay, so YOLO is about 10 times as fast?
Yes, it's 10 times as fast almost. The only bottleneck that we've got is that the camera isn't only maxed out at 30 or 60 FPS. So that's the bottleneck. YOLO goes even faster than the camera.
Okay, thank you.
Thank you very much. For this moment, we close this